everyone. Welcome to the Wednesday Chem Help ASAP live stream. So today, as you can tell from the title, we are going to be doing the big, scary topic of limiting reagents. Although sometimes just stoichiometry is scary. But we're going to be going over limiting reagents. We're going to, of course, just like we always do, I'm going to start with a simple example and then we're going to work into more complex problems. Now, I think I have probably prepped more problems than we're going to get through in an hour, but I wanted to make sure that we had enough. Also, in these problems, of course, we will do a gram to gram problem, but I also mixed in a little bit of concentration, some density, and some gas laws problems too. Again, so you can see different kinds of limiting reagent problems. As always, if you have a question, please feel free to post it in the chat, and I will try to remember to turn and look at the chat and make sure I keep track of any questions that come in. These problems can be difficult, but bear with me. We're going to take this very systematic, very step by step. And again, in our first easy problem, I hope you can see that it's not this completely new wild concept that you've never heard of before, but actually you have been thinking about this kind of concept in just everyday life. All right, with that being said, let's jump into our first problem. All right, so this is what I kind of call my real world problem. You need to set up tables and chairs for a party. Each table needs 4 chairs. In the storage closet, you find 15 chairs and 4 tables. How many complete tables can you put together? So this is not what you think of when you think of, oh, I need to do a stoichiometry problem or I need to do a limiting reagent problem, but the concepts are going to be exactly the same. So what I want you to see is, even though you may have never set up tables and chairs before, is the concept and the techniques are the same as what you have maybe done previously when you were, I don't know, maybe you're putting together something else or planning a party or anything else. So what I'm going to do first is I'm going to set up a balanced chemical equation. You're like, tables and chairs, what? But let me show you what I mean. So my equation is going to be 1 table plus 4 chairs is going to give me 1 complete table. Now, these numbers obviously are very simple. You have probably already calculated how many complete tables you can make. But what I want to show you is the technique that we are going to use for limiting reagents as we move forward with more chemistry-related problems. Okay, so what I want to do first is I'm going to try to figure out, here's my balanced chemical equation. I want to figure out which of my 2 reagents, either the tables or the chairs, which are going to run out first, so that I can figure out how many complete tables I can make. So I'm going to run actually 2 tests. So this is my testing phase, and I'm just going to pick one of my items to test first. It doesn't matter which, we'll actually test both of them. So I'm going to go ahead and start with my chair. So I am going to test my chairs, and the question I'm asking is, all right, I have 15 chairs in the storage closet. How many complete tables can I make with those 15 chairs? So I'm going to set this up very much like a stoichiometry problem. So I have 15 chairs, and I want to convert from chairs to tables. So I'm going to use my stoichiometric coefficients. I guess I wouldn't call this a mole ratio because we're not dealing with moles here. So there are 4 chairs for every 1 table. My chairs cancel. I'm left with table. And so I need 3.75 tables. That's how many tables I need. Now, how many tables do I actually have? How many are in the storage closet? There are 4 tables in the storage closet. So I have extra table. So my tables are in excess. So I have extra table. If my tables are in excess, it means my chairs are my limiting reagent. So I just write LR up there to say that my chairs are my limiting reagent in this problem. Okay, but let's say you didn't test chairs. Let's say you tested tables. We can absolutely do that. So in the storage closet, I had 4 tables. Again, I'm going to use my stoichiometric coefficient to convert between tables and chairs. So for every 1 table, I need 4 chairs. Again, tables cancel. So I need 16 chairs. So 16 chairs needed. Okay, so I need 16 chairs. In my storage closet, how many chairs do I have? I only have 15. I don't have enough. I am going to run out. So again, my chairs are limiting. So my tables have extra. My chairs are limiting. Again, we've already labeled this as the chairs are your limiting reagent. This is a limiting reagent problem. This is stoichiometry with limiting reagents. Again, you probably did this calculation super fast in your head. You didn't even think about it. But the technique you used is actually limiting reactant. So let's predict how many complete tables we can make. So starting with my limiting reactant, we're going to predict complete tables. So using my stoichiometric coefficients. For every 4 chairs, I get 1 complete table. Oh, sorry, not 4 chairs. 15 chairs. And we've actually done this calculation, but that's 3.75 complete tables. Now, when we're dealing with moles, having a fraction of a mole is totally fine. But when we're dealing with complete tables, I can't have 0.75 complete tables. So I have 3 complete tables plus 3 extra chairs. So hopefully, again, that makes sense. So that is how we test for our limiting reagent, which one of our 2 items in this case is going to run out first. And then we predicted products. Okay, so we know which one's going to run out first. So let's use that one to predict how much of our product we can actually make. And actually, we calculated our excess as well, which we're not going to do in this live stream. Okay. All right, so good. OG Benchmarks is on. And yes, there is always a little bit of a lag when we do a live stream. Let's go on to our next problem, our first real chemistry problem. But again, I don't want you to leave those concepts behind, but recognize that we're going to use the same thing moving forward. Okay, so this question is, let's see. Okay, good. I wanted to make sure my face didn't totally obscure this. How many grams of zinc chloride are formed when 10 grams of zinc react with 10 grams of hydrochloric acid? So this is a classic limiting reagent problem where you are given the same mass of your 2 reactants and asked to determine which one is limiting, because the thing that you're going to want to do initially is say, well, I have 10 grams of both. So you'd either say both are limiting or neither are limiting. I'm going to react the same. I'm going to get 10 grams of product. But remember, grams is not the same as counting atoms or molecules. We need to go to moles to do that. Just like with the tables and chairs, you wouldn't want to weigh. You wouldn't want to start with how many kilograms of chairs you had or how many kilograms of table. You need to know how many of your items. And in chemistry, that's going to be moles. So our first step here is to convert our grams to moles for both of our reagents. So we have 10 grams of zinc. So that's a pretty easy conversion. We're just going to use the molar mass here. 380 grams of zinc and 1 mole of zinc. Okay, so we have 0.15295 moles of zinc. Now, before we move on, we are going to keep track of our sig figs. So in this problem, we have 3 sig figs in our 10 grams, and we have 5 sig figs in our molar mass. So we should be rounding right here to give ourselves 3 sig figs. Again, don't round yet. Keep extra decimals moving forward. We're going to round at the very end. All right, so that is our moles of zinc. And we also had 10 grams of hydrochloric acid. I should have written the zinc smaller. So molar mass here is 36.458 grams of HCl and 1 mole of HCl. So I'm just going to put this down here. So this is 0.27428. That should be enough mole of HCl. Again, I'm going to mark where my sig figs should be. This is 3 sig figs in the 10 grams. And again, we've got 5 here. So I should have 3 sig figs. So again, I'm just going to mark at that third decimal right there. Okay, so now that I have moles of both of my reagents, I'm going to run the test just like I did with my tables and chairs example. So let's run the test. And I think I'm actually going to switch colors for this test just so hopefully it makes it more clear how I'm organizing this. Okay, you, again, just like with the tables and chairs, you can test either reactant and it will tell you what the limiting reagent is. We will end up testing both of them just so that it confirms that you have the correct limiting reagent. Now, when you're practicing or you're doing homework, it's great to run the test on both of your reagents and just confirm that yes, you have picked the correct limiting reagent. However, if you're in a timed situation like on a quiz or a test, then know that you don't have to test both. You can just test one and it will tell you what the limiting reagent is. But for our sake, because we're not under a time crunch, we will test both. All right, so let's go ahead and test our zinc first, just because I converted that to moles first. Again, it does not matter. So I'm taking my moles of zinc. And the question I'm asking is, for all of my moles of zinc to react, how many moles of hydrochloric acid am I going to need? So I'm going to use my stoichiometric ratio between zinc and hydrochloric acid to figure out how many moles of hydrochloric acid I would need. Again, this is a test calculation. This is a theoretical calculation. If I'm going to use all of this, like if I'm going to use all of my chairs, how many tables do I need? If I'm going to use all of my tables, how many chairs do I need? This is your theoretical calculation. So using my stoichiometric ratio, make sure the moles of zinc cancel. This is 2 moles of hydrochloric acid. Again, I'm getting these numbers just in front of the balanced chemical equation, and that gives me my stoichiometric ratio. So this is a really easy calculation. 3059 moles of HCl. This is how much hydrochloric acid is needed. Now, what we need to do is we need to say, hey, okay, so we need 0.3 moles of hydrochloric acid. How much hydrochloric acid is in the storage closet? Well, this much hydrochloric acid is in the storage closet. So I need 0.3059 moles, but I don't have enough. I only have 0.27 moles. So I am going to run out of hydrochloric acid first. So my hydrochloric acid is limiting. I don't have enough. So I also, especially when you're first starting limiting reagents, label, label, label. So I'm going to label my hydrochloric acid up here as LR, limiting reagent. And I like to put a box around it as well, or a circle or star or something to say, this is your limiting reagent. Because moving forward to predict products or to predict excess, we need to always start with our limiting reagent. Now, obviously we've identified our limiting reagent, but let's run through the calculation as if we started with our moles of hydrochloric acid. Again, it should confirm the same limiting reagent. So let's say instead of testing your moles of zinc, you decided, no, I think I'm going to test my moles of hydrochloric acid. So starting with my moles of hydrochloric acid, the question I'm asking is, if I'm going to use all of my moles of hydrochloric acid, how much zinc do I need to have? Okay, so make sure the hydrochloric acid, so it cancels. Oh, you know what? I should say that canceled 2 there, just so we're clear. And this gives me 0.13714 moles of zinc needed. All right, so if I'm going to use up all my hydrochloric acid, I need to have at least 0.13 moles of zinc. Okay, let's go to the storage closet. How much zinc do I have? Oh, I've got plenty. I've got 0.15. I have extra. I have excess zinc. So zinc is an excess, which again means that hydrochloric acid is limiting. So you can see how both of your tests are getting you to the same answer, and that is what is key. Okay, so our final step, now that we have identified our limiting reagent, is to calculate our grams of zinc chloride. And this is pretty easy. All we're going to do is a very simple stoichiometry problem. But at this point, again, it's really critical that you use your moles of limiting reagent. And this is why I like to label everything carefully here. So notice you've got a moles of hydrochloric acid here and a mole, oh, sorry, that should be mole, not mo. And you have a moles of hydrochloric acid here. This moles of hydrochloric acid, remember, this was your test. This was your theoretical calculation to see if you had enough. But this moles, the one that's in a box, that is how many moles you actually have. Again, with the tables, you'd say if I had 4 tables, I need 16 chairs. But how many chairs do I actually have? I only have 15, so I don't have enough. So again, make sure you are labeling things, you're writing things in a way that makes sense to you so you can make sure that you use the correct number of moles moving forward. So I'm going to start with my moles of my limiting reagent. That is 0.27428 moles of hydrochloric acid. And again, this time I'm going to be predicting products, and which one did it want? It wanted zinc chloride, so I've got to predict my zinc chloride. So let's do my mole ratio of hydrochloric acid to zinc chloride. And it's asking for grams, so we have one more conversion factor here. And that is just the molar mass of zinc chloride, which I do have here. It is 136.286 grams of zinc chloride. Okay, so put this in your calculator. And just like usual, I'm going to give multiple decimal places because we need to figure out our sig figs. So let's do sig figs. So starting with my moles of hydrochloric acid, remember I marked where I needed to round for the correct number of sig figs. I'm going to mark that again down here. So my starting, and let's just do this in different color. My starting moles, I have 3 sig figs. Of course, my mole ratio has an infinite number, and my molar mass here is 1, 2, 3. It has 6 sig figs. So I need to round to 3 sig figs for my final answer, which means I'm rounding right there. So my final answer is 18.7 grams of zinc chloride. Okay, any questions? Nope, no questions. All right, that's fantastic. I hope you guys can see that grams of zinc chloride at the bottom there. I'll try to organize the other problems a little bit better. Okay, so that is a limiting reagent of grams to grams. Let's go on to our next problem. Okay, when copper reacts with nitric acid, nitrogen monoxide is formed. If 35 grams of copper react with 350 milliliters of 1.2 molar nitric acid, how many grams of nitrogen monoxide will form? All right, so the other thing that I didn't talk about with the other problem, and I should, is let's first identify this as a stoichiometry problem, and then let's identify this as a limiting reagent stoichiometry problem, because that is important that you can identify what type of problem you're dealing with so you know what tools you're going to need. Actually, I'm going to go to my laser pointer here. So the first question is this a stoichiometry problem, and how can we tell? Well, we can tell because I am given information about copper and nitric acid. So I'm given information about actually 2 compounds, but I am asked about a different one. So I'm asked about nitrogen monoxide. Now remember, for stoichiometry, it doesn't have to be reactant to product. It can be reactant to different reactant. It can be product to a different product. It can be product back to reactant. But the key thing is you're given information about one or two compounds and you're asked information about a different about a different compound. Now let's identify it as a limiting reagent stoichiometry problem. And the way we know that is we have been given information about both the copper and the nitric acid. So we're given information about copper and nitric acid. So once you're given information about two or more reactants, because some reactions might have 3 or even 4 reactants, then you know you first have to identify your limiting reagent. So this is a stoichiometry problem, and specifically it is a limiting reagent stoichiometry problem. Okay, and we have a balanced chemical equation, which obviously is very important as well because we use mole ratios all over the place, and you want to make sure that your reaction is balanced so you have that correct mole ratio. That is the thing that teachers and professors love to put in there as just a double check. Okay, I'm going to give you a reaction, but you need to make sure that you balance it first. Now, for us, this reaction is already balanced because I want to dive deep into the actual limiting reagent part. So just like with our other problems, we need to first convert to moles, because remember, once we're converted to moles, and once we're talking about moles, then we're actually talking about the number of either atoms or the number of molecules, which is so critical. So my first conversion will be easy. I just need to convert my 35 grams of copper. So let's do that first. So this is 35 grams of copper. And the molar mass of copper is 63.546. So again, remember when you're using your molar masses, they should have more sig figs than whatever number you start with. Okay, so our moles of copper, again, writing out plenty of decimal places. Moles of copper. And I have 3 sig figs here, and I have 5 here, so I should be rounding to that decimal right there. Again, not going to round because I don't want to do rounding. I don't want to introduce rounding error. Now I need to deal with my nitric acid. So I'm not given grams here, so we're not doing a molar mass calculation. We are given a volume and we're given concentration, and specifically we're given molarity. So if you remember, molarity equals moles of solute over liters of solution. But you can also, I want to show this, you can also set this up more like a conversion factor. So let me show you how to do that. You can always plug and chug into that equation there. If that's the way you're most comfortable doing it, by all means do that. But one thing that I like to do is, because molarity, again, is moles per liter, this is the same thing as 1.2 moles of nitric acid over 1 liter of solution. So this is molarity. It's just written with its 2 units specified instead of just its 1 concentration unit. And now it's easy to see I can get my liters of solution to cancel. I just got to convert my 350 milliliters into liters. That's easy. I'm just moving the decimal 3 places to the left. The only thing I want to be careful with is, remember, this 0 here is significant. So when you're converting and you're counting sig figs, you have 2 significant zeros there at the end of that number. And this equals, I did this calculation, here we go, 0.42 moles of nitric acid. Okay, so let's do sig figs for this. So I have 2 sig figs here. This one is considered exact, so it's infinite. And I have 1, 2, 3, 4 sig figs here. So I need 2 sig figs in my final answer. So I'm going to round right there. Now, just for argument's sake, let's say you needed 3 sig figs. You would simply add a 0 to the end of that number, and that 0 is automatically significant because it is to the right of the decimal and it is to the right of a significant digit. But we didn't need to add that 0, so I am going to erase that 0. Now that I have moles of both of my reactants, I'm going to run my tests. So let me switch back over to the green. So here are my tests. Again, I'm going to run both, but you really only need to run one. So let's start with my moles of copper. So I have 0.55078 moles of copper. Again, the question I'm asking mathematically is, if I'm going to react all of that copper, how much nitric acid am I going to need? So I'm going to use my stoichiometric ratio between my copper and my nitric acid. Again, always make sure you're writing your units down. It is so easy to get these stoichiometric ratios backwards. And then you're going to end up with either a situation where you think both are limiting or both are in excess and you get really weird stuff. So just make sure you write your units down, and that'll prevent all of those problems. Okay, so doing this calculation, I get 1.468 moles of nitric acid. Again, this is how much is needed to react all of my copper. So this is, again, my test. This is my theoretical calculation. All right, so I'm going to need 1.4, almost 1.5 moles of nitric acid. Let me go into the storage closet. How much nitric acid do I actually have? I only have 0.4. I don't have nearly enough nitric acid. So that means that my nitric acid is going to limit me. It is limiting. Again, I'm putting a box around my moles of nitric acid up here, and I'm going to put a big LR right there by the nitric acid in my chemical equation. Okay, so let's say that you decided not to test your copper. Let's say you wanted to test your nitric acid first. That's totally fine. So starting with moles of nitric acid. Again, the question here is, if I'm going to react all of my nitric acid, how much copper am I going to need? Well, let's use our stoichiometric ratio. 3 moles of copper. Again, our nitric acid cancels, and this gives us 0.1575 moles of copper. So I need at least 0.15 moles of copper. Let's go to the storage closet. How much copper do I have? Oh, I've got plenty. I've got extra copper. I have more than enough. So copper is in excess. Again, which means that nitric acid is our limiting reagent. Okay, now that we know our limiting reagent, we can do our stoichiometry. We can actually answer the question that the problem asked us. And so the problem asked us how many grams of nitrogen monoxide are formed. So again, starting with my limiting reagent, what I boxed or starred or highlighted, however you want to do it, I'm just going to run through my stoichiometry. So there are my moles of nitric acid. Now I am predicting product. Okay. So first let me get my moles down here of nitric acid. This is what I want to cancel, and I want to predict nitrogen monoxide. So that is a 2:8 ratio. Okay, so that is going to get me 2 moles of nitrogen monoxide, but the problem asked us for grams of nitrogen monoxide, so I need my molar mass of nitrogen monoxide. So there, and the molar mass is 30.0061 grams of nitrogen monoxide. Okay, so now my moles have canceled. I'm left with grams. Great, I have just need to put this in my calculator, and I have answered my problem. Plenty of decimal places, and now let's figure out how to do our sig figs and where to round. Okay, so starting with our nitric acid, so I was going to round at that hundredths place, so I'm going to put my mark under here. So I have 2 sig figs, and my first number, of course, infinite in the mole ratio, and 1, 2, 3, 4, 5, 6 in my molar mass, so I should go to 2 sig figs right here. So my final answer, whoops, is not 1. Not sure why I wrote that, is 3.2 grams of nitrogen monoxide. Okay, let's make sure there are no questions. Nope, I don't see any questions. So now let's go ahead and go on to our next. So now we've done concentration. We're going to be dealing with density here. All right, again, you can see we're kind of mixing and matching not only limiting reagents, but kind of the different ways you'll see these presented to you in problems. So let's just read it first. And sorry, that many there is being kind of blocked by my picture. Sorry about that. Okay, calcium chloride is formed when calcium carbonate reacts with hydrochloric acid. How many grams of calcium chloride will be produced when 25 grams of calcium carbonate reacts with 100 milliliters of concentrated hydrochloric acid? And then as an aside, we get the density of concentrated hydrochloric acid is 1.190 grams per milliliter. So as we did before, let's first identify this as a stoichiometry problem, and then let's identify this as a limiting reagent problem. So how do we know it's stoichiometry? Well, we are given information about calcium carbonate and hydrochloric acid, and then we are asked about how many grams of calcium chloride. So again, given information about one element or compound and asked information about a different element or compound, and we can connect these with a balanced chemical equation, which of course is right here. So yep, we've got our balanced chemical equation. So we know it's stoichiometry. How do we know it's a limiting reagent stoichiometry problem? Well, we were given information about calcium carbonate right here, and we were also given information about hydrochloric acid right here. So we have information about two of our reactants, so we need to figure out which one is limiting, which one is going to run out first, because that is going to limit how much product we can make. To do stoichiometry, what unit do we always have to be in? Yes, we always have to be in moles. So our first step is converting into moles for both of our reactants, or both of our reagents. Let's do the easy one first. Let's do the 25 grams of calcium carbonate. So I have 25.0 grams of calcium carbonate, and using the molar mass, which is 100.0869 per 1 mole of calcium carbonate. Again, our grams cancel, we're left with moles, and that gives us 0.24978 moles of calcium carbonate. Okay, let's do sig figs before we move on. I have 3 sig figs here, and I have 3, 4, 5, 6, 7 sig figs down there, so I'm definitely rounding to 3 sig figs right there. Next, let's deal with our hydrochloric acid. Okay, so we are given a volume, and just like the last problem, you'd say volume and concentration, we can handle that. We know the formula for molarity, but this time we are given volume, but we're given a density. So we're going to have to do this a little bit different. Again, I'm going to set this up as a conversion factor, but you can always use the formula that density equals mass over volume, and plug and chug there and get a mass out and then convert it to moles. But if I can, I like to string together all my calculations in one, so I'm not doing one step and then doing the calculation and then doing another step. I like to do it all at once. I call it smashing, if at all possible. So I'll show you how I'm going to smash this calculation. Starting with my 100 milliliters of hydrochloric acid. I want to cancel my milliliters. Ideally, I'd like to go to moles, but I can't go straight to moles. However, I can go from milliliters to gram using the density, because density helps us to convert between volume and mass. So I just want to make sure that my milliliters ends up in the denominator here. So it's 1.190 grams of hydrochloric acid per 1 milliliter of hydrochloric acid. That is true anytime you have units written like this. The number goes with whatever units in the numerator, and in the denominator, you always assume that is 1. So in this case, that would be 1 milliliter. So that is going to get us to cancel our milliliters. We're left with grams. And now we're just converting grams to moles, which is just molar mass, right? So that's easy. So this is 36.458 grams of hydrochloric acid per 1 mole of hydrochloric acid. So now my grams have canceled and I'm left with moles. So again, this is how I do my smashing. I took milliliters, I used density as a conversion factor, and then I used my molar mass as my final conversion factor to get to moles. But again, if you prefer to use the formula density equals mass over volume and get to your mass that way, and then in a second step convert to moles, that is absolutely totally fine. We will get to the same place. Okay, so let's actually write down this number of moles. So that is 3.26403, and that is moles of hydrochloric acid. Let's mark up our sig figs. So our 100 here has 4 sig figs. That 0 is significant. My density has 1, 2, 3, 4 as well, and I have 1, 2, 3, 4, 5 in my molar mass. So I need 4 sig figs. So 1, 2, 3, 4. I'm going to round at that 4. Okay, I have my moles of my calcium carbonate and my hydrochloric acid. That's fantastic. Now it's time to run my tests to figure out which one of these reagents is limiting. Okay, so let's test this out. Again, I'm going to run through the test for both of the reagents, but you only have to do one. So let's start with our moles of calcium carbonate. So I have about 0.25 moles of calcium carbonate. If I'm going to use all of that up, how much hydrochloric acid do I need? Okay, I need my stoichiometric ratio between calcium carbonate and hydrochloric acid, which thankfully is given to me in my balanced chemical equation. And that is simply a 1:2 ratio. Now, with these simple ratios, again, it can get very easy to drop writing your units, but almost invariably when students start dropping those units, they start using the wrong ratio. So in this case, we're multiplying by 2, but if you don't put your units in, it's really easy to start dividing by 2 instead. And then we've got mathematical problems, which leads to major confusion. So even though I know it's difficult, I know it takes longer, make sure you keep writing those units down. Okay, so this is 0.49956. This is how many moles of hydrochloric acid I need. Okay, so let's go to the storage closet. I need about 0.5 moles of hydrochloric acid. How much do I actually have? Oh, I've got 3.25. I have extra. I have excess. So my hydrochloric acid is in excess, which means my calcium carbonate is my limiting reagent. So I'm going to box this, put an LR over here. Actually, because I have space, not an R. I keep writing the wrong thing first. Label this as limiting reactant. Again, you want to make sure that you're pointing yourself to your limiting reactant. This one is limiting. Use this number of moles. Okay, but let's say we didn't test our calcium carbonate. Let's say we tested our moles of hydrochloric acid. Let's just run through that calculation. 3.26403 moles of hydrochloric acid. So if I'm going to use all of my moles of hydrochloric acid, how many moles of calcium carbonate am I going to need? Again, using the mole ratio between the two of them. This time I am dividing by 2, and I get 1.6320 moles of calcium carbonate needed. Okay, so I need 1.6 moles. Let's go to the storage closet. How many moles do I actually have? Oh, I've only got 0.2. I don't have near enough. So my calcium carbonate is limiting, which of course we already knew. But again, it's nice to get that confirmation that yes, both of your tests are pointing to the same limiting reactant. I've run out of space, so I'm going to need to give myself an extra page here, which is not surprising. Let me just add one in there. And now what I want to do is I want to do my final stoichiometry, but let's go back and reread the problem. So I know I'm starting with my moles of calcium carbonate because that's my limiting. And then I want to know how many grams of calcium chloride, which is right here. Okay, fantastic. This is a 1-to-1 ratio. This is like the easiest and best ratio. So starting with my moles of calcium carbonate, 978 moles of calcium carbonate. Oh, that 3 looks funky. My mole ratio is 1-to-1. Mole of calcium chloride. And then, of course, because it asked for grams, I need one more conversion. I need to convert to grams. So I'm just going to use the molar mass to do that. And the molar mass is 110.98 grams of calcium chloride per 1 mole. And so that gives me, with lots of decimal places, grams of calcium chloride. And now let's determine our sig fig. So I need to go back to this page. So for our calcium carbonate, we rounded at that 9. So let me go back here and put my mark in. So I have 3 sig figs in my moles of calcium carbonate. I have infinite in my mole ratio, and I have 1, 2, 3, 4, 5 in my molar mass. So I'm rounding to 3 sig figs, so I'm going to round right there. So my final answer is 31.0 grams of calcium carbonate. Again, you want to make sure you have that 0 there because you want to make sure your reader understands that that tenths place is a significant place. So that is why the 0 stays. If you just wrote 31, that would only be 2 significant figures. And remember that 0 is significant because it is to the right of the decimal and it is to the right of a significant digit. Okay, let's make sure there are no questions. It looks like we're okay. And we have time for one more. We can do one more. Oh yeah, this is a gas one. Actually, because we've got time for one more, I am going to skip this one. I want to go to my other gas one because this one is a little more difficult. So this is how many grams of potassium oxide can be produced if 2 grams of potassium react with 0.25 liters of oxygen gas at 855 torr and 12 degrees Celsius. Okay, we have a balanced chemical equation. Let's first identify this as a stoichiometry problem and then a limiting reagent problem. So it is stoichiometry because I've been given information about potassium and I've also been given information about oxygen, but I have been asked information about a different compound, specifically potassium oxide. And I can link all of these compounds with a balanced chemical equation. So that makes it stoichiometry. Now, the fact that I have information about potassium, which is one of my reactants, and information about oxygen, which is my other reactant, makes it a limiting reagent stoichiometry problem. Of course, when we're doing stoichiometry, we always want to be in moles. So that is our first task, is to get everything into moles. As usual, let's start with our easy one. Start with our grams to moles, no problem, right? So I have 2 grams of potassium. So let's use that molar mass to convert. So that is 39.0983 grams per mole. So my grams cancel. I'm left with moles, and that is 0.05115 moles of potassium. Okay, so for sig figs, I've got 3 sig figs here, and 1, 2, 3, 4, 5, 6. So I am going to round to that second one right there to give myself 3 sig figs. Again, remember, this 0 right here is not significant. Yes, it is to the right of the decimal, but it is not to the right of a significant digit. You can also think of this as if you were to convert this to scientific notation, would you keep that 0? And you wouldn't keep that 0. All right, that was just my aside there. Let's get, so that's moles of potassium. That's our easy one. But now we need moles of oxygen. Okay, we are not given grams. We are given a volume. So can we use a density or a concentration? No, we don't have a density or a concentration. We have a volume, a pressure, and a temperature. So what do we need to use? Ideal gas law. Okay, ideal gas law. PV equals nRT. So let's just plug in what we know, and we might need to adjust as we go. So pressure, we have been given a pressure, that's 855. 855 torr. Do we have a volume? Yes, we have a volume, 0.250 liters. We do not have N, that's our number of moles, that's what we're trying to solve for, so I'm not surprised we don't have N. For R, what generally drives R are your pressure and volume units. In this case, I have torr and I have liters. So my value for R is going to be 62.36367, and that is liter torr per mole K. And my temperature, I do have my temperature of 12 degrees C, but I've got a problem. That is Celsius, and my R tells me my temperature needs to be in Kelvin, as it always is when we deal with ideal gas law, but it can be a little bit of a reminder. Check your units of R. It will help you remember to convert your temperature from Celsius to Kelvin. So I need to convert this Celsius to Kelvin. Of course, that is very easily done. I am simply going to take my 12.0 degrees Celsius plus 273.15. I'm going to have to squeeze this in right here, and that is 285.15. 85? Yes, okay, just make sure I'm reading my handwriting right. The one thing I want to be careful here is sig figs, because I've just done a conversion, right? And I've done an addition. So you want to use your addition subtraction rules. That means you're looking at number of decimal places, not total number of sig figs. So my 12 degrees Celsius went to the tenths place, and my conversion factor went to the hundredths. So my final answer should be rounded to the tenths place. It should be rounded to that one right there. But again, as always, I'm not going to round until I get to the very end of the problem. Okay, so now I'm going to put my temperature in here, again with my little reminder, and just make sure that all of your units cancel. So my torr cancels, my liter cancels, my Kelvin cancels. I am left with moles. That's exactly what I'm solving for. I'm solving for N, which should be in moles. So everything is working out. Okay, so actually plugging this in and solving for N, I get an N of 120,199. And again, this is moles of oxygen. So all of this information we put into ideal gas law was pertained to oxygen. Again, it can be easy to throw in the moles of potassium here if you're not really careful about writing your units down. But in your ideal gas law, you want to make sure all of the numbers you put in pertain to the same gas. So this is my moles of oxygen. Let's talk about sig figs. So I've got 3 sig figs in my pressure. I've got 3 sig figs in my volume. I have a ton of sig figs in my R, 1, 2, 4, 5, 6, 7, which is good. You never want R to limit you. And then in my temperature, I have 1, 2, 3, 4 sig figs. So I am limited to 3 sig figs, which means I'm going to round to that 0 right there. We did a lot of work for just getting our moles, and I already need a new page, don't I? So let's get a new page, and let's run our tests. So we can start with either one that we want. I just generally start with the one that I converted first, so I'm going to start with my moles of potassium. So starting with my moles of potassium, I want to figure out, if I'm going to use all of my potassium, how much oxygen am I going to need? Well, using the mole ratio of potassium to oxygen, Again, I'm getting this from this balanced chemical equation right there. My moles of potassium cancel, and I'm going to need 0.01279 moles of oxygen. Okay, so I need 0.012. I have 0.012. Oh, I need to go to the third decimal place. So this one is really, really close. So I have 0.0120, but I need 0.0127. So I have not quite enough. So I'm going to need 0.0127, and I only have 0.0120. So I am going to run out of my oxygen. All right. So we're kind of running out. All right. So what I'm going to do at this point is I am going to just go ahead and jump straight to my stoichiometry. So starting with my moles of oxygen, I was like, where are they? Okay. And I have 0.012019 moles of oxygen, and I have been asked to convert to grams of potassium oxide, so that is a 1:2 ratio. 2 moles of potassium oxide. And again, because I need to convert to grams, I need the molar mass. And that is 94.196. Okay, so my moles have canceled. My moles of potassium oxide have canceled. I have grams. And this is 2.4090 grams of potassium oxide, but let's do sig figs. Oh, so I need to go back. So I was supposed to round at that 0, so let me give myself my little mark here. So I have 3 sig figs here, infinite in my stoichiometric ratio, and 1, 2, 3, 4, 5 in my molar mass. So I'm rounding to 3 sig figs. I am rounding to right there. So my final answer is 2.41 grams of potassium oxide. Okay, so that is limiting reagents and dealing with concentrations and dealing with density and dealing with gases. And the one problem I skipped was also with gases, but they were gases at STP, so you can use the molar volume to get to moles of that. So I hope you found this helpful with your limiting reagents. Again, I know it can be difficult, and there are a lot of calculations to do and a lot of calculations to keep track of. Make sure you're organizing it in a way that makes sense to you, and make sure you keep writing down those units, even though I know it's easier just to skip everything, but trust me, writing down your units is going to save you a lot of trouble in the future. Let's just make sure there are no more questions there. And I hope to see you next week. As always, if you have a request for a topic, something that you're going over in class, and you want to see some more examples and you want to ask questions, please just feel free to contact me. You can email me, you can leave a comment on this live stream, and you can also message me on Facebook. So I hope you guys have a great rest of your Wednesday, and I'll see you next week. Bye.